Hello everybody and welcome back to another Universe Sandbox video. In this video we're going to be talking about orbits and parking spots in space. Places where you can park your spacecraft and know what'll be there in maybe 10 hours time. So yeah, it's gonna be pretty interesting. We're gonna cover a lot of different orbits, and yeah, to get started with, I just thought I would show a rough model of what space looks like. As you can see, there's a lot of satellites clustered in this kind of low Earth orbit area. We also have the Geo ring, and yeah, as you can see, there's a lot of satellites up there. A lot of stuff just whizzing around. The collision is bound to happen at some point with all that stuff whizzing around there, so that's why it's important that we try and clean up space. But anyways, let's go ahead and cover some orbits. So yeah, first off, our most basic orbit is gonna be our standard low Earth orbit. So anywhere from like 100 kilometers to 2,000 kilometers above the surface, that is kind of what you would call your low Earth orbit, anywhere within this general area. As you can see, we got the satellite here, and it's just whizzing around having a good time. Now, not all satellites are like this. So this is an equatorial orbit. This satellite is going on the equator. Most satellites are actually going to be a bit tilted. Because if you take a look, any satellite launched from Florida is not going to be equatorial by default. If you launch due east from Florida, your satellite's actually going to be going in an orbit that looks kind of like that. That's launching due east from Florida. So due east from Florida, satellite kind of goes that way. Which is weird, isn't it? And yeah, it's just because, well, Florida's the best place to launch from the US. If you want an equatorial orbit, obviously there's the French Guiana spaceport. But yeah, really, for most purposes, this is fine. This kind of orbit is fine for most purposes that you need a satellite for. Science satellites, basic Earth monitoring satellites will just kind of go into this orbit, and they'll be fine here. Obviously, if you launch from, like, Russia, for example, they're going to have a more inclined orbit. Their orbits are actually going to be about 45 degrees inclined, so they're even more inclined when launching from Baikonur. And again, that's why the ISS is at a 45-degree orbit. As you can see, if you were to launch from Florida, actually, I think Earth is a little bit... Yeah, Earth is a little bit tilted, but as you can see, launching from Florida, if you launch up 45 degrees, you can get into this orbit. And yeah, that's why the ISS is at a 45-degree orbit, because otherwise, Russia could not participate. That's the lowest they can launch to. So yeah. Now, if we're continuing along with inclinations, we can keep going up and up and up until we get to a polar orbit. As you can see, a polar orbit goes up and over the poles, and over the course of multiple orbits, this will cover most of the Earth. As you can see, as the Earth rotates under this orbit, the satellite is flying over. So yeah, really great for Earth's observation, weather satellites, all kinds of satellites where you would want to see most of the Earth at any given time. This is the kind of satellite you want to launch. Now, I just so happen to position it in a point where we're right on the Terminator line, but if you imagine this to be an actual system, and not just in space with nothing else around it, except for the moon. Hi, moon. But anyways, if we throw the sun in here, and make this a more realistic system, as we progress time, we will see that as the Earth orbits the sun, the spot that's illuminated is going to move out from under our satellite. As you can see, there it goes. It's being moved out from under our satellite. However, there is a way to counteract this using something called a walking orbit. Now, usually in most simulations in games like Kerbal Space Program and stuff, this isn't something that you can really do. However, in Universe Sandbox, we have the option to turn on a non-spherical gravity. And this is because walking orbits are caused by something known in the scientific community as fat Earth theory. The Earth, as it spins, becomes a little bit more oblate at the equator, meaning that there's different gravitational pulls as you fly over the equator. So if we put ourselves into a very eccentric orbit, and maybe even make it a little bit inclined as well, we will notice that over the course of this orbit, it should kind of precess over the course of a very long time because of that oblateness factor of the Earth. So over time, this eccentric orbit is going to kind of make its own orbit. And it's also, the inclination's going to go all wonk. It's going to kind of just do its own thing. But this can be harnessed. This can be harnessed in a good way. And the next orbit we're going to talk about uses this oblateness factor in order to keep a satellite in a position where it is constantly under the sun. And that is where we lead to Sun-Synchronous Orbits. Meaning that if we put this satellite back right here on the terminator line, and we put it in a slightly retrograde orbit, so let's say like 92, ever so slightly retrograde, we will notice that as we go along, the satellite moves as the sun moves. Although it looks like I'm doing it in the wrong direction. I might have put the Earth in a retrograde orbit instead. There we go. Okay. So now we should be processing in the right direction. As you can see, it's processing. And we are actually outpacing it a little bit. But that just comes down to fine-tuning the inclination of the orbit. But yeah, there you go. That is a Sun-Synchronous Orbit. Again, it's processing too fast here, but you get the idea, right? Like, the orbit would process at the same rate as the sun processes around the Earth. I'm just not good enough to get it exact. But you get it. You get the idea. I don't need to dwell on this for much longer than I already have. But, speaking of dwelling, what if we talk about an orbit that dwells over the same position of Earth all day? And that would be a geostationary orbit. So, about, like, this far away, I believe, is what we would call geostationary height. Basically just... oh, that's way too far, actually. Basically the height that equals 1 day. This is like halfway to the moon. So there you go. Not as nearly far as I had it before, but there you go. There is your... ah! Sorry, too fast. Too fast. Simulation speed is too fast. But anyways, there is your geostationary orbit. It's around the same spot of the Earth. You can see that we are staying roughly at the same spot. This would probably be more so considered a geosynchronous orbit. As you can see, the Earth is kind of wobbling. And these were the first orbits to be launched to this altitude. Because again, like I said before, Florida is at a high inclination. So you would have geosynchronous orbits at a 28-degree inclination. Because that's what they could launch to. It wouldn't be until much later when we would have more powerful rockets that could do like a dogleg maneuver or just, you know, launch from French Guiana. But yeah, if we go ahead and adjust this thing's inclination, we can get it to be in a true geostationary orbit. Rock steady in our position right here. Look at that. Rock steady. Now, geostationary is good and all. After all, you don't need a satellite dish with tracking. You can just set a simple fixed satellite dish on the ground. It'll point at the satellite that's floating right above. And, yeah, the job's a good one. But, as you can see, if you live up north, the geostationary satellite's not really going to be able to reach you. As you can see, like, Canada is basically just off the charts here. Like, we can't see Canada. Russia would be too high as well. So, what are they going to do for their communication satellites? Well, what if we just take them and put them over the top?
My goodness, what an idea. Why didn't I think of that?
So this is a Tundra orbit. Now, in reality, Tundra orbits do have a bit of eccentricity to them as well. They usually have an eccentricity value of 0.2 or 0.3, so that way they spend a little bit more time up and over the poles. But in reality, a lot of time is still being spent underneath the Earth, where not really much is going on. They spend a decent amount of time up top, but you got pretty much just as much time where they're out of range and you can't exactly see them. So what's exactly the solution? A Molniya Constellation. So as you can see, this constellation of satellites helps with some of the problems that the Tundra satellite had. So if we go down onto the ground track and we watch a satellite, well, that one's going down. Oh, but that one's going up. So we're going to track that one. We're a satellite dish. Beep boop, tracking it, tracking it, tracking it. Oh, and as that one goes down, another one's coming up. Another one's coming up. We can track that one. We can track that one. We can track that one. Oh, but then that one's going down. Oh, but then we can track. We can track the next one. There it is. Again, my timing for these is probably a little bit off, but there we go. There's another one. Let's see if I can't get these a bit better. All right, there we go. I think I fixed it. I didn't quite have the eccentricity right. Alrighty, so now if we check out this orbit, let's track this satellite right here. Okay, so we are a ground station. We're tracking this guy. We're tracking him. We're getting good readings, good data. And oh no, it's setting. Oh, but then that one's rising. Right then. Perfect timing for you, buddy. We're going to track you now. Gonna track you now, track you now, track you now. And if that one sets, that one's coming across. And then as that one sets, I should have one rising right here. There it is. There it is. A little bit late, buddy, but still pretty good. So yeah, there you go. There's your Molniya orbit. And that gives you constant high-latitude communications. And yeah, that was developed by the Soviets. So yeah, pretty cool. And it looks pretty cool as well, watching all these satellites kind of trade off positions. Like, no, you're good, traded, as I whiz around the bottom side here. And then, oh, I'm here, just in time for this guy. Pretty cool. And now, before we get to the parking spots in space, there are two more orbits that I would like to talk about, and that is a medium Earth orbit and a high Earth orbit. So anyways, to start with, MEO would be around this height. So this would be your medium Earth orbit height. And yeah, this orbit is commonly used for GPS satellites, because you do get a lot more coverage per satellite at this height. So yeah, you know, a little bit higher than low Earth orbit, but not quite out to geostationary. Just for the record, geostationary is about that height. So as you can see, it's about halfway between the two. Now, beyond geostationary, we actually have high Earth orbit, which is used very rarely, mainly for scientific research and military applications. There you go. So that would be maybe some high Earth orbit satellites there for you. Look how it like goes in and bounces out. Boing. Very mesmerizing. Very fun to watch. Boing. Anyways, we should talk about Lagrange points now. The parking spots in space, more commonly known as Lagrange points. So here we have a simulation created by Big Byte, which shows the L3 point, the L1 point, the L2, L4, and L5, all marked with spherical cows. So yeah, these would be positions in real life where you could put a spacecraft, leave it there, and then come back to it later. Unfortunately, in Universe Sandbox, it doesn't quite work that way. As you can see, if I play this simulation out for any amount of time, the L1 and L2 points just go away. L5, L3, and L4 stay relatively stable, though. But yeah, L1 and L2, they're just gone. So maybe don't trust those too much. I do believe the JWST at the L2 point does need to do some basic form of station keeping in order to actually stay there. But yeah, this is basically the Lagrange points. Yeah, they're the parking spots in space. As you can see, you left your cow here. It's still here. You know, I wouldn't, yeah, again, wouldn't trust L1. It seems like he's going for a little ride. But yeah, again, the L4 and L5 are very well simulated in Universe Sandbox. So if we actually hop into this simulation... Oh, and crashed the game, apparently. But yeah, if we play this simulation by Geoffrey Legrix, we should be able to see the L4 and L5 points appear out of the ring. Is speed this up a little bit, and as you can see, there's L4 and L5. You can see kind of where they're bunching up, where the particles are bunching up. Those would be your L4 and L5 points. They're not getting much closer to Earth than pretty much exactly there and there, which is pretty neat. I mean, there might be some stuff that's kind of getting thrown around the L2 point, but nothing's really staying there. Same with the L1 point. Nothing's really staying there. And L3. Yeah, nothing's really bunching up over there. Because, yeah, again, L4 and L5 are the most stable of the Lagrange points. So, I would trust those. I would trust those. I would park there. And, again, we do have another simulation by Bono4. That, again, also shows the L4 and L5 points. If we speed this up a ton, we can see that the L4 and L5 points stay there. They kind of have the most particles, which again, this is actually what sort of happens around Jupiter. A lot of asteroids from the asteroid belt find their way into Jupiter's massive L4 and L5 points. Yeah, if you imagine this is the sun, this is Jupiter. Maybe the sun wouldn't be this big, and then this would be all the asteroids from the asteroid belt being funneled into Jupiter's L4 and L5 points. Yeah, actually we can maybe hopefully see that a little bit. Let's go ahead and add the asteroid belt to the sun, and we'll see if any of them get sucked into Jupiter's L4 and L5. And it looks like there might already be some in there. Already. Yeah, you can kind of see these. The game has already put some there, but we might see some more get sucked in. I know if we move the asteroid belt out, that definitely would happen. So maybe we just put it right on Jupiter. See the L4, L5 point. L4, L5. Might actually got the wrong, probably L4, L5. Again, not entirely sure, but yeah, those are your parking orbits, your parking spots, and all the other orbits as well. We covered polar, regular, geo, pretty much everything. I can't really think of any other orbits that I've missed. So if you guys enjoyed this video, please be sure to leave a like. If you learned anything, maybe subscribe. Because yeah, I do have a lot more space videos planned in the coming months. So yeah, you're gonna want to hit that subscribe button if you don't want to miss those. And also, please consider becoming a member. We have a Portal 2 playthrough going on right now. We just wrapped up the main games. We're moving on to multiplayer. So if you guys want to see that and antics in other games that I don't usually play, feel free to hit that join button down below. And until next time, I'll see you around. Bye-bye.